Hello everyone. Let me introduce you the next talk of Priyotosh Bandyopadhyay from the Indian Institute of Technology, Hyderabad. That will talk about perturbativity, Higgs, mass, first order phase transition, and gravitational wave with inert model.
Okay, thank you. So first of all, I would like to thank the organizer, Tathagata, Anish, Mohanty, and Koushik, everyone. This is my first visit to ICTS. Unfortunately, I have not been so well, but I try to collate some of the older work. About the new work, probably I'm not going to say anything because the results are not out and there are more stringent constraints coming. But I'll shed some light on the thing that I'm planning to do. So there's also a typo that Anish pointed out. This is Shilpa, Shilpa. So these are, she is my PhD student now, is in Pohang and as a postdoc. So these are some older work. So let me go through my plan. So I'll try to motivate the extended scalars, especially the inert model like inert singlet, inert doublet, and inert triplet from the excuse me, from the vacuum stability point of view. And then we show that if you extend these sectors, you can have a rescue and you achieve the electric stability of the vacuum. And more or less, these works were done after 2012 of Higgs discovery, and there are many works on the vacuum stability and the uncertainty of the top mass and the Higgs mass. And but a few people actually also put work on the perturbativity. So we looked into the perturbativity bound on the dimensionless couplings, and we found out that as introduction of new quartic couplings gives you the vacuum stability, there is also an additional set of bounds that come from the perturbativity. And then we will look into the phase transition possibility and the first order phase transition possibility in this scenario. And typically we know that there are two parameters, a bare mass that you introduce the scalar and Higgs portal coupling. These two are the most instrumental in governing the first order phase transition. And we'll look into the perturbativity sector again, try to see whether these couplings are constrained by the perturbativity more than what your first order phase transition requires. And then we'll talk about these corrections at two loops. These corrections means, first of all, the beta functions at two loop, which would differ from beta function at one loop. And the perturbativity constraints also changes from one loop to two loop. And there is slight change in the thermal potential if you consider the two loop thermal potential. In that case, the mass bound also changes a little bit for the triplet case. We'll mention that. We'll show some benchmark scenario where you can observe some gravitational wave signal. And later part, I will mostly concentrate on the work that we are doing, but we are not mentioned in detail. So especially the 2022 or 23, I don't remember, the Atlas result on Higgs 2 gamma gamma, which is very, very precise. So even the models which are inert, but if they are from higher representations of SU2, namely the doublet and the triplet, they have a charge Higgs and they contribute in this Higgs 2 gamma gamma, and they constrain the scenario a lot, basically the portal coupling, which is instrumental for your first order phase transition. So the fate of the inert model or inert models in general for first order phase transition is not very promising at the moment, but let's go through it. So as I said, like this is a famous vacuum stability plot. This is a standard model metastable region. And if you add a scalar, you probably get stability. Considering inert model that you expect a scalar that will give you the dark matter candidate, which will serve the purpose. And then you also can address the first order phase transition, that dynamics. So you want to kill 3 birds by 1 extra scalar, which is inert. This is the basic motivation. So let's first focus on the vacuum stability. Excuse me. So let's look at the standard model. The standard model, you have a large top Yukawa coupling, and if you take the contribution of the beta function, then you see that the quartic coupling gets a negative contribution proportional to the Yukawa to the power 4, and this causes negative correction. And because of this negative correction, this lambda, running lambda, can go to 0 at some point. And you can have a certain scale mu equal to capital lambda, for which this goes to 0. From there, you can calculate a lower bound on the Higgs mass. This is pretty well known, standard textbook thing. This can be analyzed in a kind of Coleman-Weinberg effective potential approach, where you write down the potential as lambda effective, like say you are only considering the h direction, so h to the power 4, and the lambda effective has all the quantum corrections. So in the wonder quantum corrections, you have the tree level values. Then you have, this is for the standard model. So you have the, top W, the gauge bosons, and every other particle that can contribute would go here. So studying the lambda effective would give you a measure about the stability of the potential. And what people have realized, so there could be 3 possible cases. This green one, the green patch, where you have only one minima, and lambda effective if is greater than 0, this is the stable condition, so you are in more stable condition. Then you have a lambda effective is greater than this quantity but lesser than 0. In this case, what happens, there is a transition probability for a deeper minima, but the rate of the tunneling rate is more than the age of the universe, so you have not tunneled through the deeper minima, but in future you would. This is actually given by this yellow patch called metastability. And if lambda is more negative than this, then you'll have a runaway solution. And this is a famous Stumia slide I took. So the ideal world, we want a Mexican hat. This is what the textbook says. But what you actually get probably is a dog ball. So you might tunnel through, or you go to a runaway solution. So this was the standard model with a SM Higgs mass at 125.5 GeV and top mass around 173.2. These results are pretty sensitive to this top and Higgs mass, and you can see here. You can see here. So we are kind of here, and if you vary the top and Higgs mass, then your region can change, and these are depending on the scale. So where do we lie? So ideally, we would be happy to sit in the greener region than the yellow region. And there are models beyond standard model scenarios like right-handed neutrinos, or let's say seesaw, type 3 seesaw, inverse seesaw, where you introduce fermions, which also couples to the Higgs boson. Now these fermions, when they go through corrections similar to the top quark, they also give negative corrections. So when you extend those your scenario to fermions with that couples with the Higgs, you would go more to the radial region, which actually I studied that, but in today I'll not discuss that. But if you, on the other hand, if you add a scalar mass, scalar spectrum in in the model, you will push towards more greener region, and this is what you expect. So the first one, so this I already mentioned, that what is a rescue. The rescue is basically you have to have the scalars that will enhance the corrections and more positive corrections, and then you can have more stable scenario. So this is one of the typical plot that I found. This is a long work. So this is, if you look at this, this is around 10 to the 9 GeV. In the standard model, it was going to be negative. But if you add a singlet, which is a Z2 odd singlet here, then you enhance the stability from the standard model. So now look at little bit non-trivial representation of SU2, which is one of the famous scenario till date, which is the inert Higgs doublet. So you have two Higgs doublets and the inert triplet. So inert so in the case of type 1, you just do not have the M12 square term, so it becomes inert. So you have both the doublets phi 1 and phi 2, and then phi 2 does not take a wave because it's Z2 odd, and because of that you have a dart multiplet. So you have a pseudoscalar, a heavy Higgs and a charge Higgs. They sit in the Z2 odd part of the spectrum, and everything is Z2 even. So, and either of these pseudoscalar and the scalar can be dark matter, and you have an enhanced scalar spectrum in the scenario, and that could give you a positive correction to the lambda effective, and you would expect the vacuum to be more stable. But if you look at in the standard model, you have only one lambda, which is lambda 1 here, but now you have lambda 2, lambda 3, lambda 4, lambda 5. We are considering CP conserving scenario, so we do not have the lambda 6, lambda 7 terms. But additionally, like you have 4 additional quartic couplings, and so that would play a little more role. Now, if you just consider the other non-trivial representation of SU2, which is the SU2 triplet y equal to 0, then you have additional lambda t and a portal coupling of Higgs is lambda ht. But in this case, you have two components, was T0 and T plus minus. T0 is the neutral one. It can be the dark matter candidate. And T plus minus, it can actually have decay to pion, soft pion and T0. This is very difficult to detect because the mass splitting comes from the loop corrections, which is around the order of 166 MeV. So it has lesser degrees of freedom, but more or less it can also address the same issue. So what we do, so we write down the effective potential, and then we add the SM part in the lambda effective, and as well as the contribution from the inert doublet and the inert triplet scenario, where all the Higgs contributions are included. Now let's look at this scenario. Why? Because in the standard model we know that the stability is compromised. It is going lambda is going to 0. So if we put all the lambda i's, so this lambda I not equal to 1. So lambda 1 means the SM like lambda. And for inert triplet case, lambda ht is the lambda I not equal to 1. And in case of doublet, these are lambda 2, lambda 3, lambda 4, lambda 5. So there are 4 of them. So when I'm saying lambda I not equal to 1, that means there are 4 of them for inert doublet and lambda ht for inert triplet. So if you put a very small value like 0.01, then what you find is that the effect is minimal, it's not visible. Then you raise it to, let's say, 0.06. You see the doublet part is getting kind of more positive. That is because they have more lambdas to play a role, more degrees of freedom. And at some point when you choose a value of 0.068, you see this is like almost like a tangent, and the IDM becomes like stable, but ITM is still crossing the region which is negative and again coming out. But if you put all the values as 0.1, you achieve the stability for both the cases. So it just says that, okay, you have a scalar and you just tweak the quartic coupling a little bit, and then you achieve the stability. And this can be seen from this graph for the IDM. We are in the completely green region. For ITM, we have a little bit in the yellow region. And the contribution, why it is happening, is also available from here. So if you look at the evolution, this is a one loop, and these plots are actually a two loop, but the two loop expressions are really big. I think I have it at some point, but here in this case, if you see the contributions, in the case of triplet, it is the only one portal coupling that is affecting, and in the case of doublet, these are the coupling. They're contributing to the evolution of the SM-like quartic coupling lambda 1. So, so these two papers are kind of that I wrote with Shilpa and Gopal and Arjun and Shilpa and Manimala are kind of also very interesting, because these are the fermionic extension, and the vacuum becomes more unstable if you introduce these fermions. So to enhance the stability, these scalars could be handy, and they can also provide the dark matter. So, but today I'm not going to talk about these two works. So far so good. What we find is that if we extend the scalar sector with enough quartic coupling, with a little enough value, then we can achieve the vacuum stability. So we are happy. Now, is there any upper bound on this scalar quartic couplings? Of course, yes. So let's consider typically this lambda I should be less than 4 pi, and the GIs I'm not plotting here. Also, GIs are gauge couplings. Also, GJs, sorry, are less than 4 pi. Now, this is for inner doublet. So this is for lambda 3, lambda 4, and lambda 5. And again, this lambda I not equals to 1, because lambda 1 is kind of fixed with the Higgs mass. And if you look at, if you have a 0.01, this dotted line corresponds to Planck scale perturbativity. So you can have Planck scale perturbativity till here, but if your lambda 3 is above, let's say 0.6 or so, you are compromising on the perturbativity of the lambda i's. Now, if you start with the electric value of 0.1, then the perturbativity actually you loses the Planck scale perturbativity here. But if you choose lambda equal to 0.4 or 0.8, then what is happening is that you do not have Planck scale perturbativity. Rather, perturbativity scales are below 10 to the power 10. So if you choose a very large enough electroic lambda isoquatic coupling of the order of 0.4 or 0.5, that means your theory is no longer perturbative till the Planck scale. So the problem that you are trying to solve of Hakon stability till Planck scale is again compromised. So there is a fine balance when you try to tweak the stability. You have to also check the perturbativity. And this is the same feature you can recast at lambda 4 and lambda 5, and the behavior is more or less the same for inner doublet. Now, if you come to inner triplet case, remember here there is only one portal coupling, that is lambda HT, and one self coupling, that is lambda T. So the number of quartic coupling is much lesser than the inner doublet case. So this is the Planck scale perturbativity, this hashed line, and then you see all the others actually satisfy the Planck scale perturbativity, But if you choose a sufficiently large lambda t, which is greater than 0.3, then around 0.5 it will also lose the Planck scale perturbativity. So the inert triplet model is more safe than the inert doublet case because it has little more range of pushing to the electric scale lambda I compared to the inert doublet case. So any question from here? No? Okay. Anyway, so this is what I actually said, that the Higgs quartic couplings are kind of restricted by both the stability and the perturbativity. Now let's come to the other motivation, which is the first order phase transition motivation. So so I mean, electric baryogenesis is one of the main motivation that people are talking these days, which requires first order phase transitions. And if it is first order phase transition, then the Higgs mass, if it is standard model, it should be very low. The crude calculation would give you around 50 to 70 GeV, and we observe the Higgs mass at 125 GeV. So they also need some scalar extension that can simply give you first order phase transition. So again, the first order phase transition can happen if you extend the SM sector with a scalar, and if you have an inner scalar, it can also provide dark matter. So you can think of it as a win-win situation. So let's try to see a toy kind of scenario. So at the high temperature, the potential looks like this, but this causes a second order phase transition. And if you need a term, which is a phi cube term, then you can actually get the first order phase transition. Now, in the standard model case, this E is kind of very low, is around 0.01. So if you calculate the Higgs mass with this, is around 49 GeV. But in the standard model case, the lambda equals to kind of well known is 0.13. So which gives you a Morse crossover, not a first order phase transition. So electric baryogenesis scenario cannot be explained within standard model, and it is a beyond standard model phenomena. So let's consider the simple inert singlet and the triplet extension. I'll mention the doublet at the end. So in the singlet case, you have S, which is SM singlet. Now you have one portal coupling here, lambda S HS, and a self coupling lambda S. This is Z2 odd, and S can be a dark matter. Similarly, you can have a triplet, SU2 triplet y equal to 0. You have lambda HT as a portal coupling and lambda T as a self coupling. So if you compare these two couplings, they are kind of similar in number. Both of them has one portal and one self coupling. So you write down the thermal potential like the usual prescription. You calculate the thermal masses, and basically, as I said, they satisfy this, and you expect this first order phase transition, electric baryogenesis, and gravitational wave from there. Let's see. So the way we actually, so let me just stop here. So the way we try to treat this is that not usual study of the just the gravitational wave and the parameter space. Rather, what we looked into that, what is the dependency of the portal coupling and what is the dependency of the perturbativity. So next few slides, I'll go from one to another, just to reiterate the fact that that basically there are some restrictions from the perturbativity even in this case. So in order to do that, so we write down the potential in terms of this polynomial, and you calculate this T1 and T2 temperature, and T1 and T2 are kind of crucial in determining. So this is the case of the singlet case. This is the triplet case. These are for different soft mass parameters, and these are lines where T1 equal to T2, and above which you expect the first order phase transition, below which you expect the second order phase transition, and this is the self coupling that is being varied. So you see there is a very minimal dependency of the self coupling when you vary the masses. It is almost independent, like looks very parallel. And let's look at the region for pi plus Tc over Tc, which is greater than 1, which corresponds to, so the region above this dashed line, we expect the first order phase transition. In the x-axis, you have the portal coupling, so here is lambda hs, and here you have lambda ht. Now here we vary a different self coupling, and the bare mass is chosen to be 50 GeV. Now what we see is that as if you are here for so let's say for a so if you are here for lower region of the Higgs portal coupling, you get the second order phase transition, and you have to go above certain portal coupling to attain the first order phase transition. And as you move the self coupling from 0.0 to 0.5, you actually need more portal coupling to achieve the first order phase transition. And if you compare the triplet and the singlet, so what is happening is that singlet has lesser degrees of freedom, so it needs more portal coupling compared to here the region is less than 1.5. Here you see the region is around 1.5. So total number of degrees of freedom also matters in getting the regions corresponds to the first order phase transition. Now what we did is that we did a reverse plot where basically we have the portal coupling and we have the bare masses, but we put the self coupling to be 0 just for a simple case, and we see that as we increase the bare masses, the region is more and more to the second order phase transition, not to the first order, and you need really high portal couplings to achieve first order phase transition for higher mass values. And this is kind of very demotivating in terms of observational aspect, like from collider data as well as the dark matter data, direct and indirect both. So that I will discuss later. So what we actually saw that typically if you try to find out the singlet mass is greater than 350 GeV, the portal coupling is greater than 3, and for the triplet it's if you are looking around 400 GeV, it is around 2.6. So you need large Higgs portal couplings. Now let's come back to the discussion of the beta functions where we use this information for the zero temperature stability and perturbativity. So if you look at the beta functions here, the lambda 1, which is the SM like Higgs beta function, has a contribution which is from both the portal for the singlet and the doublet, and here is this the triplet portal and the triplet portal and the singlet portal coupling, which has also the contribution for the other couplings as well. Now, when you consider all of that, what you actually see is that depending on the perturbative scale, a maximum value can be achieved. So in the table, we put, let's say the perturbative scale is 10 to the power 4 GeV. The maximum portal coupling for the singlet is around 1.6545, and for the triplet is 1.3710. And if you go to the Planck scale, then this value is around 0.3, 0.237, and this is as around 0.218. So a lower perturbative scale would allow the higher values, and for more degrees of freedom again in the ITM compared to ISM, the values are more restricted in the case of ITM. Now, this is very, very stringent, but then there is a funny twist in the tail is that if you consider the two-loop perturbativity, there are some negative terms in the beta function that slows the growth towards perturbativity, and the two-loop limits are little bit better than one loop. So let me before going to the two loop, let me show some result whether the Higgs mass can be achieved here or not. So if you look at the left side plot, is for the singlet. So there are scales given like 10 to the power 4 to 10 to the power 19 GeV scales, and the bare mass is 0 and the self coupling is 0. Only the so the Higgs mass, we want to see the Higgs mass can be achieved at 125 GeV or not, and we find that only for the singlet you can achieve this. For the triplet with this this particular scenario, you won't meet it, the first order phase transition as well as the Higgs mass at 125 GeV. So the situation is very, very restricted. Now look at the one loop result here. So this is a kind of a 3D plot. So the 5 plus TC over TC is varied from 0 to 3.5. The bluish region is basically the second order phase transition, and this yellowish region, yellowish to orangish region corresponds to the first order phase transition. So you can see that only for the singlet case you can achieve with a very effective theory case like where the perturbative scale is around 10 to the 4 GeV, you can achieve it. So this is very, very restrictive. Now, as I said, when you come to two loop, the conclusion may change. So what happens is that in the case of one loop, the Landau pole is actually Landau pole appear to other quartic couplings before lambda 1, but in the case of two loop, it is basically lambda 1 hits the Landau pole before the other couplings. But the growth of the lambda 1 is slower, as I said before, because there are negative contribution which are proportional to lambda 1 cube and lambda 1 lambda ht square and lambda ht cube, and similar for the singlet also. And but for Planck scale perturbativity, the singlet has double the allowed parameter space here. So in this case of two loop, the lambda max is available around 4, and here it is for the triplet it is around 1.95. The contribution for the singlet, the allowed value of the singlet is more because for the triplet you have some additional positive contribution to the two loop beta functions that again runs it faster than the singlet. And I will probably flash this thing beta functions, but it looks little ugly later on. Let's see. So here we try to do an analysis where this is the singlet case, and we vary the bare mass around 5, 845, and 1000 GeV. And for TeV, for the triplet, it is 100 to 300. And this is the portal coupling verified, and we see the Higgs mass around 125 GeV here, and this is the 5 plus TC over TC. So what we want to see that is around 845, 840 GeV, and is around 200 GeV. You can achieve both the first order phase transition as well as the Higgs mass. And so if you redo this plot like a 3D plot, is the same thing like before. These are the second order phase transition. These are mostly first order phase transition. And you can calculate a limit for the Planck scale perturbativity. The singlet mass, the upper limit is you get around 840, and the triplet mass is around 193 GeV, which is pretty low. And this is very, very restrictive, and this is coming from the theory. There is no experimental observation data that is put here. So as I said, like these are these little longer beta functions, but you can look into this if you wish. So now, if you remove the Planck scale perturbativity, in general, the one loop mass bound is kind of for the singlet is around 900 GeV, and for the triplets is in 310 GeV. Now, when we calculated the thermal potential at one loop. We considered the beta function at two loop, but there is a problem in the uncertainty. The uncertainty is the one loop, the accuracy is basically of the gauge coupling to the power cube. And if you consider a two loop potential, then only you gauge g to the power 4 accuracy. And we also did that. But the result did not change for the singlet. For the triplet, the result changed by just 310 to 320. So yeah, thanks. So the result does not differ much from the one loop to two loop thermal corrections, but it's like the upper bound is very strong. So nevertheless, we plotted some points where you can observe the gravitational wave signature like other models, and just for within the allowed region. And let me just spend a few minutes on the work that that has to be revisited. This is work by this group, Rose and others. So this is the inner doublet, and they also pointed out regions which are having first order phase transition and the second order phase transition. And in this paper, what they have done, they have considered this relic abundance, and of course they also realize that it cannot be completely dark matter because it would be ruled out. So they considered different percentage of the dark matter if you go in the paper, and they found out, and they have a multi-step phase transition possible. So this is like the one I talked about, the one-step phase transition. But this bound recently came in October, this Lux-Zeppelin new bound, and this is very, very strong. And with this bound, I think the limits for the portal coupling is 5 × 10⁻³ for any mass that is less than 400 GeV. So it is that strong. So now the tweaking is not that easy. And the other bounds that are very interesting, which is from Higgs 2 gamma gamma, which I am going to mention a little bit. So these actually work in progress. So I'll just flash some slides. So this is the inner doublet, and this is the inner triplet. So there is so if you calculate the Higgs 2 gamma gamma, there is a stop loop, then W loop, and the charge Higgs loop. And for the inner doublet, the coupling is λ3, actually λ3 times Webb. For the triplet case is lambda HT. And this funnel region comes because of the sign ambiguity that you have. And this region, you need the FOPT, first order phase transition, which is already ruled out by Higgs 2 gamma gamma, most of the regions. So if you are having an inert model, no matter, so especially the inert model where we have non-trivial SU2, like doublet, triplet, 4-plate, 5-plate, you probably will hit this thing. And this is also 2023 result. And with these bounds, we find it's really challenging to explain all these things together now. There is one more thing that that actually we also saw for the inner triplet, that if you calculate the Summerfield enhancement for the dark matter relic, you are basically again the push to above TeV. So the tweaking is very difficult, like you have to find out really underabundant point to explain FOPT. The inner doublet, we are working on it, so right now I cannot say. There are many works, has been studies like this, the Cheng Wei Chan group in the inner singlet. They also address this direct dark matter constraint issue. This one of this paper, I don't know which one, they also observed this S goes to S star symmetric case where they can evade the bound. So this is quite interesting. And I have put few names, but I apologize if I miss any name for citing, because there are many works on extended Higgs sector and explaining the first order phase transition. But today I just focused on the inert models only. So please forgive me if I forget your name here. And yeah, so I am more or less done. Yeah. So to conclude, like the extra scalars are needed for vacuum stability, and it can provide dark matter if they're inert. And if you have seesaw models or any fermionic extension, then they can give you more stability. And first order phase transition, of course, is possible, but they are restricted by observation and as well as theory. And we need to look into this thing very carefully. Another thing I did not mention because of lack of time, which is the Hess-N formula, it also rules out a few points in the lower mass region. And so this is the bound I was talking about, that this is the most strong. This came in October and this last year. So, and this is it. Thanks to Gamma Gamma. Thank you.
Are there questions from the audience?
I just have a quick question. So for the vacuum stability analysis in the models with the extra inert doublets or triplets, do you recalculate the tunneling for the metastable vacuum to go out to the large field values? Or is it possible to just recast in order to draw the boundary between stability and metastability? That boundary, I guess, has to do with the lifetime of the electric vacuum, right?
You are talking about the zero temperature calculation, right?
Yeah.
Yeah. So we calculate the decay lifetime and we compared with the condition. Yeah. On the back side. Yeah.
Other question?
I was thinking about that the perturbativity bounds that you are satisfying, you are using the zero temperature calculation, right? So the upper bounds on the couplings are obtained by the zero temperature calculation.
Yeah, I mean,
do you have any idea that like if we go to the finite temperature calculation?
The beta functions are independent of zero temperature or finite temperature. So there is a theorem, I think there's a paper by Hitoshi Murayama or somebody. So beta functions would be the same. So if you are looking at the coupling variation, so it's equivalent to look at the same beta function. So we are fixing the value at the electric scale and try to see the perturbativity behavior. But of course, the effect, the thermal effect would be shown in the mass term as well as the potential term. Okay. So, so initially we took one loop thermal potential and two loop beta functions, but later on, after the referee report came, we also did two loop thermal potential and two loop beta function, and the result did not change much. Yeah. But perturbativity is independent of this analysis mostly.
Yes.
But the
and also maybe this is not that relevant, but I mean requiring Planck scale perturbativity is like assuming that your model will be valid till the Planck scale.
Yeah. So because the stability, the whole motivation that started the stability, whether we are in a metastable or not, that is the Planck scale metastability. So because I started with that motivation, I carried that motivation only. But if you look at the 840 GeV bound enhanced to 909, that is because when I removed that condition, and overall mass bound that got enhanced from 840 to 909. So I have both the results. Yeah.
No other questions?
This one's quick. Is there a Higgs invisible decay channel in these models?
Sorry, is there any?
Higgs invisible decay?
Look,
Are any of the extra scalar states stable and invisible so that you get Higgs to invisibles?
Oh, Higgs to invisible. Actually, that parameter point we did not look into, but Luigi looked into that. Yeah, so that the reference inert doublet, they looked into that, yes. And also the other reference that Cheng-Wei Chen group, the inner singlet, they have looked into one of the scenario. Yeah. You get the Higgs to invisible constraint there, yeah.
Other questions? Okay, so let's thank Priyotosh again.